Yeah, I see 17 attendees joining in. So we'll wait for another minute before we get started.
Okay.
Okay, so we are 3 minutes over. Let's get started. Good morning, good evening, and good noon to the participant and from the different time zone. A very warm greetings from IEEE CAS Circuit and System Society. Today we have a world-renowned expert with us, Mr. Kang. We call him Steve. That's how the world knows him. And this session today is special. We are celebrating IEEE week, and then we will be celebrating IEEE history week as well. So today we have this session on personal journey in circuit and systems. We'll hear about more about from Steve about this. And my name is Preet Yadav, and I'm the chair for IEEE Circuit and System Society, Delhi chapter. I'm based out of India. And we have our special guest, Steve, joining us from live from California. So Steve, welcome you to the session.
Thank you for invitation.
Okay, it's our pleasure to have you on board today. So let me quickly read through Steve's biography. And Steve's, if I want to talk about his achievement and major milestone, probably I'll take another 20-30 minutes to explain. So I picked up some of the major bullet points about all the great contributions Steve have done all this year to the Circuit System Society or to the general VLSI semiconductor community. So Steve, he's a life fellow of IEEE. He received PS degree from Fairleigh University, New Jersey, USA, and then MS degree from State University of New York, Buffalo, New York, USA, and then a PhD degree from the University of California at Berkeley. Steve, I always wanted to be in the institute, but not lucky enough like you to study at Berkeley. So Steve, he's 15th president of Korea Advanced Institute of Science and Technology, which is known as KAIST. He is second chancellor of the University of California at Merced. He worked as Dean of Engineering of the University of California at Santa Cruz and the department head of Electrical and Computer Engineering at University of Alliance at Urban. Before returning to academia, he was technical supervisor of high-end microprocessor development at AT&T Bell Labs at New Jersey and managed the physical design and manufacturing of Bell Mac 32. And we have more exciting things to be talked today about all those Bell Lab days of Steve. He's currently a distinguished professor of emeritus and a research professor with the Beskin School of Engineering at University of California, Santa Cruz. He holds 16 US patents and have authored more than 10 books. And I have a special personal connect with Steve for one of those books, and I'll probably talk about that in later part of session today. He has published more than 500 journals and conference papers, and I hope this number is now much more than 500 now. And his research interests includes memristors and memristor systems, neuromorphic computing, low-power VLSI design, and computer-aided design. Steve was president of IEEE Circuit and System Societies from 1991 to 92, and the founding editor-in-chief of IEEE Transaction on VLSI System. He's fellow of ACM, AAAS, and AAIA, a foreign member of National Academy of Engineers, South Korea, and a life member of Korean Academy of Science and Technology. He has just been elected as a member of the European Academy of Science and Arts as well. And then there are so many other accolades on Steve. So Steve, it's a true pleasure and honor, to moderate this session along with you. I'm really privileged and welcome you to, this session. That's how we greet in India for all the respectful, leaders, respectful humans, we come across. And personally, I've been in touch with Steve for a few years now, and apart from Steve's technical expertise and all the good things which we heard, he's a gem of a person. I should admit this in for today, and it's true honor and privilege to be with you, Steve. Okay, so we have about another 50 minutes in our hand, and I'll start with some Q&A about Steve from his early days toward the advanced research which he has contributed all these years for IEEE Circuit System Society or in general for VLSI and semiconductors. And towards the end, we can have a Q&A from the audience as well. And Samantha, please correct me. I assume the audience will be able to send their questions through chat to us, and I'll be able to pick up based on the time we have in hand. Okay, so let's get started. So here comes the very first, I would say question on public demand, Steve, is that, what motivated you to pursue, electronics and VLSI design back in your days? Because in those days, electronics or semiconductor or VLSI design was not that popular. And when this whole ecosystem was still, I would say, still getting built up and was still at the early stage. So what was your motivation, being into the semiconductor domain in those days?
Thank you for nice introduction and very kind of you. So my involvement in electronics started actually when I was in military service. I was enlisted in Korean Air Force right after high school and worked at a radar site to handle with very high frequency, ultra high frequency communication equipment. And in that period, I learned about more about solid state electronics. And then after entering college after military service, I started a major in electronics. That's how I got started. Yeah. Mm-hmm.
Wow, that's so interesting, from defense to the engineering. So that's quite inspiring, and that shows, it's not end of the world, where you start your career and where you end up landing. Quite interesting, and it really shows how how foresight and passion can guide career choice, even when the ecosystem was not fully ready for it, and you're still stepping in, and how you made all this way to this this particular junction. Okay, thank you. So let me move forward, Steve. Now the next question we would like to ask you is that how did your time at Bell Labs was in your career path? Okay, are there any lessons learned from those years that you still guide you? That because as we say, the fundamentals remains the same throughout the life. So, would you like to share some insight on that part, please?
Yes, indeed. when I was at Bell Labs, it was a really gold mine for new knowledge and pioneering research at that time, not only in electronics, in physics, chemistry, materials, and systems engineering as well. So I got to meet a lot of talented people and learned a lot from them through discussions and collaborations. So I was very fortunate to be in the front line of CMOS technology. That was emerging technology, and I learned about integrated circuit processing, and learned about CAD tools and their advancement, as well as telecommunication systems and computing systems. So it was truly fortunate to be at Bell Labs at that time.
Okay, that's really interesting and insightful. That's inspiring for our current students to hear. So let's move a little more further down in your journey, because you are a great mix of industry and academia. You started with industry, and then being in academia for such a long time. So since you've worked in both industry and academia, for students who are just starting out, and who are still in their academia, maybe doing their bachelor's or master's or a doctorate degree, could you explain what these fields are all about and why they matter? Why this? I would say, even if someone wants to be in academia, why there's a good relevance of starting with industry, so that you learn those tricks and tactics, what it requires, and then coming back to academia, so that when it comes to, we talk about industry ready engineers. Okay, everyone wants the engineers to be ready on the day one, but at the same time, if the the professor is not having those insight, worked in industry, in the real day projects in industry, so that brings brings a little gap between what we teach in class and what actually is being happening in the industry. So since you have mix of experience from both of the sides, we would like to know your view about and little guidance to the engineering students who are still doing their curriculum courses.
Yes, so thank you for that excellent question. So usually we talk about always the industry versus academia and so on. But in my opinion, they feed each other. So academic research benefit some industrial advancement. And also industrial advancement also give new problems and new challenges to academic research. So I think cross-fertilizing each other is enormously important. I had the opportunity to work first in academia, and then I'm moving into industry, worked there for nearly 10 years, and back to academia. That has benefited my career a lot. I learned very precious new knowledge from industry, especially in high tech, and also guided me to guide my own students in classroom and research. In advanced technology area, industry often is ahead of academia in terms of equipment and new problems. So having interactions between industry and academia is enormously important. So when I guided my doctoral students, usually during the summertime, I ask them to take internship in industry. So my students used to take internship at the Intel Corporation, Texas Instrument, AMD, and many other companies. And not only they test what they know in industry and gain significant experience, they come back with a good feedback on how to improve their research, and so that research outcome is more impactful for a real world situation. So I always advocate cross-fertilization. Also, many professors, when they take a sabbatical leave, after 5 or 6 years of in-depth research and education, many choose to go to industry to learn about new problems and also gain significant practical experience and come back. And when they teach, it broadens their vision and how to also guide the student, because in many cases students work in industry, so we don't want to have them not knowing significant problems. So yeah, to me, industry experience and academic experience, they feed each other, and there should be frequent visit to each other, and getting feedback from industry experts on research is very important. So in the US, Semiconductor Research Corporation, which is a consortium of all the major industrial companies and their representatives, we do have a SRC research grants, and yearly they come review their research outcomes, and that has been tremendously beneficial to both the students and faculty members.
That's really great, Steve. You explained it so well. Thank you so much for this. So that explains. Really, this explanation really helps simplify things for students who are new to these domains, because ultimately both needs to go hand in hand. We need to have the next edge, next level of products, and those innovation and research, they happens in labs. And then again, it takes a while, from a lab research to an actual end product. Okay, and that again is a journey. And the more familiar you are, the better you will be while you are doing those innovation and researches in the lab. So thank you so much. And we want more and more such kind of combinations where people have both experience in industry and academia, and then they work together to take things to the next level. Thank you so much. Okay, so let me move forward. So the next question to you is, in VLSI design today, what do you see as the biggest bottlenecks? Whether these are the EDA tools, these are verification or validation strategies, or these are talent, or the growing complexity of architectures, or maybe I would say the tech nodes, because people are talking about, okay, like I started my career at 360. I'm sure you must have started your career with a much a matured node, and then 360 to 180 to 90 to 65 to 45, 40, and then 28, 14, 10, 8, 7, 5, 3, 2. And now people are, curious to know whether it is 1, 0, -1, -10, and what not. So there are advancements happening in each of these spheres, be it EDA, be it design, be it verification, validation, be it, the architecture, or be it, on the talent side of it, which is again a new angle, coming up with time, that, okay, we would need so many thousands of, trained engineers in semiconductor and VLSI. So what is your take, how this whole, whole ecosystem, is shaping up, and what is the biggest bottleneck in your terms?
Right, yes. So thank you for the good question. I think at any stage, there is always a great challenge in doing new things. And when you are at the forefront, maybe it's not, this experienced case, because you are doing it for the first time in many situations like that. So CAD tools may not be ready, test machine may not be ready. A lot of things are so new. So at the same time, the hardware design, especially in VLSI design, is pushed by new applications. In current situation is AI, for instance, artificial intelligence, which is exploding in terms of the rapid rate of change. It's much more than Moore's law, for instance. So how do we tackle this growing complexity? And at the same time, we keep on hearing that energy consumption is so much when you have a big data center, a nuclear power plant. Scale of this energy is needed. So the challenge is not only design complexity, but how do you manage energy consumption? And that is a high challenge. And then how do we improve? How much can we improve? And one golden standard is a human brain. I think we talk about neuromorphic computing, which tries to mimic how human brain functions with such low energy. For instance, the typically is said that maybe with the 20 watt of power consumption, we do a lot of brain operations. We do parallel processing, reasoning, memory, etc. So, can you create such an engine with advancement in technology? So that's the high goal. And in the meantime, power dissipation is still high. We have significant issues in thermal engineering. Is the chip is getting too hot. So how do we cool down the chip? And how do you handle more transistors on a single chip or chiplets, for instance? So handling design complexity is all very challenging issues. And that trend, I believe, will be continuing. We will have continuously enormous challenges. At the same time, in real world, there are a lot of different things. It's not just the CMOS alone. We have a photonic technology, optical links. So how do we merge optics with the silicon, for instance? So bringing all the fiber linker to the chip boundary can be an interesting issue. And yet also there is a new technology such as a memristor technology. So how can we merge memristor technology with the CMOS, hybrid technology type of things? And so there are a lot that we don't know yet, a lot to be developed in terms of CAD and design methodology and the testing and the verification type of things. So it's good for engineers. We want to be challenged.
That's right. That's right.
A lot to
So
be done.
there's a very real perspective on the challenges of modern chip design, Steve, and as you said rightly, it is not only what is there inside the silicon, okay, and it's a lot about how do you power all those big silicons, and you nailed it right that with the increase in the data center and all of this digitalization, we'll have billions and billions of devices on this earth, and each of them are connected, each of them are interacting with each other, and they have so much of data being dumped. So we need places to store them, to segment them, and to make a good interpretation out of it. And the power required for this data center is like, I think we'll be at a junction when we will have to take a call whether we want to power up a whole city or just powering up a single data center. That is a quantum, quantum of energy, we are talking about. So it's not only the story inside the silicon. There's a huge story outside the silicon, and thank you so much for putting it out in the right perspective. There are bottlenecks and everything. So thank you so much, Steve. This is quite exciting. And before I get to the next question, okay, and I want to take a pause, and I want to reflect little of my, at least my own learnings in this semiconductor sphere, where you as a author for one of the books really shaped up my career. So I just wanted to share this one quick picture, Steve, which we took a couple of years back, and I hope you recall this picture. This was back in Monterey, California. And I want to let audience know that Steve, he's author of this famous CMOS digital integrated circuit book, and I personally benefited a lot from this book. This was one of the first books, Steve, I read during my master's in the first semester, and that really helped me out to to have my fundamentals right at the right place. And let me confess this on this platform, that when I met you initially, I was not knowing you are, because I always knew you as a Steve, not with your full name of Kang. And after I think few months, I could realize you are the same author who made my life a great semiconductor journey, reading a book which is authored by you. So thank you so much for this precious gift. It is well preserved with me, and I'm sure you are role model for many of us. And there will be many thousands of such students who have taken benefit from all the good work you have done all these years. So with this, now I'm gonna change my gears a little bit, because these days, whatever we are doing, there's AI element getting into it, starting from, in India, we are popular, we are known for drinking a lot of tea, and people now talk about, AI, how do have a different flavor of tea coming in? Okay, so AI is entering in every single sphere of our life, every single walk of our life, and certainly, to the semiconductor and the technology world as well. So I want to now ask you a question, giving a little perspective towards AI. That how do you see AI and machine learning influencing the next generation of designs, and not only the designing of chips, but the whole workflow, how we do craft these chips now, how you think AI is gonna influence this whole workflow, whole whole, I would say, ecosystem about the semiconductor chip designing.
Yes, thank you. It's amazing how AI is progressing in everything that we do, not only in education, but in industry as well. And especially in the field of electronic design and design automation and so on. I always thought the most effective way of interacting with the machine will be through verbal communication. For instance, instead of using keyboard, you just talk to machine and the machine will talk back to you, respond in words. So we can translate that situation into VLSI design, for instance. So can you talk to the design machine with an intelligent machine? You just tell the machine what you want to design, and then it can produce mask, for instance, in ultimate situation. And I think someday it will be done. Through this language communication that can be achieved. In between, there's a lot of layers, right? What to be done in the first stage, second stage, etc. Then at the end, how do you know whether such a product is correct? And the verification is a big issue in that regard. So, if we scale up, it can be enormous size of a level of integration. But how do you know? How do you test what this is completely correct? I think that will be enormous challenge ongoing. Even current situation today, I think when you talk about the reliability of a machine, whether that machine is totally reliable is still unknown. I experienced that through manufacturing experience at the Western Electric in old days. And the more you know what's going on, the more you feel uncomfortable because it's not perfect science. Yet, we've been fortunate to make it work. So it's a similar situation. So with the AI and machine learning, you can handle very complex design, and you have an end product. But how do you know whether that's perfect? How do you know it will not have accident, for instance? So that's an ongoing challenge, and we need to keep working at it. Maybe we need another, a father AI or mother AI, which will check the son AI type of a situation.
This is quite fascinating, Steve. It's clear that AI is not just about only software or hardware, but it is reshaping the whole world altogether. And I just loved your last comment, that for this little baby AI, you need a father AI or a mother AI to keep an eye, whether AI is doing the job right or not, because it says that there's a boss of a boss. Okay, so we need the boss of the boss for this whole AI related things which are happening day in day out amongst us. So Steve, we are halfway through. We still have more 28 minutes to go, and I want to do a little pause here, and I want to shift to something which was really well announced, and is going to get celebrated later this month, as you were mentioning to me earlier today on the call. That please tell us more about the recently approved IEEE milestone. Those were proposed by you and were sponsored by CAS. The new IEEE milestone developed by the Bell Mac 32 microprocessor, where you yourself worked around 1976-82. So, help us to learn more about this new IEEE milestone, and feel free to use any slides if you think that would help to explain this better.
Yeah, I'll be glad to. So if you can let me share my the PPTs. Let's see. I think this may be the PPT I want to share. Share. Yes. So let me see. I can share this one. Let's see.
Yeah, we can see your PPT, and if you can go on full screen, that would be great.
Is it full screen?
Not exactly, Steve.
Okay,
Can
hold
you
on a
click
second. Let me
on,
see.
It's
Full screen. Yes. So yeah, this is the Bell Mac 32. And this is the first slide, microprocessor history. Started in 1971 with the Intel microprocessor, and then Bell Mac 32 started 1976 to 1982 development that phase. And this is first the Bell Mac 32 prototype that I was involved in. And then this is an end product with chips and other peripheral chips as a chipset. So, we worked together to achieve this milestone. And in particular for historical documentation, I worked with the Michael Condry, who is a IEEE fellow, life fellow, who worked on architecture aspect, and then Victor Wang, who worked on verification aspect. So I like to share the story. This is a very famous picture, actually. This is a Calcom plot. It's a, this 6 meters by 6 meters in scale. It's a huge plot. Why do we need that plot? Because at that time, CAD tools were not ready for chip verification. So we had to generate many, many Calcom plots. I think there are more than 60 pieces. We scotch tape them together and use them for verification. So I will tell you the interesting story on it. But this is a part of this development team. There are a lot more than 100 people were involved. But I like to highlight a few things. This is Alexander Graham Bell at AT&T Bell Labs, the main lobby. His bus is there. And then this is Bernard Murphy, my boss at the time. There's a Murphy's, the yield model is well known. He's the one from originally from England, but he was department head at the time. Here's Lou Perillo. Perillo and Payne created the twin top CMOS technology. He was Bob Cranback, very intelligent supervisor at the time. He's a Larry Nagel, who created the SPICE program. He was at the Bell Labs, who created the advice program, more advanced version of SPICE. Here's Basang Chawla, who created the MOTIS timing simulation program. And here's Alex Lopez, who was AMTS, who created what is called the gate matrix layout. He's a very talented layout designer. Steve Law, who was very talented designer and also software developer, and so on. That's me standing here. Next to me is Masakazu Shoji. He actually, the success of this project is due to Masakazu Shoji's enormous effort in SPICE simulation, clock tree tuning, and all that. So a lot of people contribute to this project. The milestone cites the 6th world first is a first full 32-bit internal and external transfer mechanism in this microprocessor. And many chips didn't have a full 32-bit internal and external. So that's the first that. We introduced domino circuits, CMOS domino circuit to reduce the gate delays. We explore the twin-top CMOS process for power efficiency and performance. Also, we realized the interconnect is important. So we have an interconnect-centric logic design. It's not the other way. It's not logic first and interconnect, but you figure out what the interconnect is going to be and then adjust the logic design accordingly. Gate matrix layout for dense layout, and then instruction to support Unix operating system and C programming. So that's the 6th world first. So yeah, that marked the milestone. This is organization. We have a system management, a system architecture type of a thing, chip architecture, design of a logic, verification effort, and silicon design, physical design, and the CAD support. And then manufacturing at the AT&T, Western Electric, Allentown, Pennsylvania at that time. And this shows, in one slide, not only this the 20 feet by 20 feet Calcom plots, 6 meters by 6 meters Calcom plot, but first a prototype. We designed a data path, very dense, well operating data path, and then control logic. But it's rather loose. We underestimated the complexity of a control logic. But initial, the control logic complexity was only 200 logic gates, but it grew to 2,200 logic gates when you implemented all the necessary things. That was not good for CAD tools. The placement and routing program called the LTX tool, that time, all the most advanced the placement and routing tool couldn't handle 2,200 standard cells. So we had to divide into 1,100 and 1,100. So you see that there's a junction here, right in the middle. You did this one first, and then this one second, and then merged them together. As a result, the wiring was not well done. And as a result, chip speed was not good enough. Original target in 3.5 CMOS technology was 4 megahertz, but actual chip speed was much less than 4 megahertz at that time because of all this wiring. We learned the lesson. That's how we said, okay, interconnect is important. So we came up with a design, interconnect-centric design. As you can see, all the PLAs were designed very closely, and then a very dense layout in the control logic compared to dense layout here. Data path is pretty much the same. And in the next generation, 2.5 micron CMOS, goal was 6.2, but it was running at even 9 megahertz for enormous success. Oh. And because of that, IEEE Micro designated the Bell-Mac 32 as a champion. See, this is HP microprocessor, Intel microprocessor, National Semiconductor, and so on. But it's among all the super micros, the Bell-Mac 32 was champion. this shows what went on this Calcom plot. I was a project coordinator for this physical design. I asked the people, please take off your shoes, like as this gentleman did. Here is your color pencil. Trace all the signals, whether there is no broken wire or not. We found many, many errors in design automation. We found many broken wire lines of which we had to fix, actually. So that was a very interesting exercise. Yet we achieved the error-free mask and had enormous success in this design. It's very memorable in that regard. This goes on more technical detail, twin-top CMOS, co-optimization of design rules for high density. Usually in the established technology, you just accept the design rule and do the layout, but we were at the forefront. So I negotiated the design rule with Lou Perillo, who was in CMOS processing. Hey, we don't need this design rule. This can be violated, okay, and so on, which helped a lot in achieving high packing density with a better performance. Domino CMOS circuit, which is well known for compact layout and in almost zero delay in pull-up because of a pre-charging. And then, as I mentioned, interconnect management, right? Interconnect centric logic design. We also did a wire sizing to reduce RC delay. We used the gate matrix layout and in matrix style, like here. This is logic, and then you have a matrix style layout. That's why it's called the gate matrix layout. We tuned all the clock tree to minimize the clock skew. And we did the transistor sizing for all the clock signals and the critical data path and so on. This shows a domino circuit, and this shows a twin-top CMOS, for instance.
Wow.
And this shows the importance of the interconnect centric. So before doing all the detailed design, we estimate the block size, we do the layout, see what the wire length is going to be, and based on that, you adjust this logic to achieve high packing. That was enormously important. Yeah, but we were at the forefront of this routing parasitics and coming up with interconnect-centric logic design. Yeah, so that was the key. Now, in a big project, there's so many things are happening. You have to have not only project meeting, but you have a daily goal, what to achieve. So I was doing the, this project management, and I was inspired by this well-known the book by Frederick Brooks, so ex-IBMer, and then University of North Carolina, Chapel Hill computer science professor. He written a book called Mythical Man Month in 1975. This is the book. In one of the chapters, he talked about how come a big project can be delayed by 6 months or even a year. And the answer was 1 day at a time. You have a delay 1 day, and then next delay, and it piles up to become several months delay, for instance. So I was inspired by that one. You have to achieve each day, and then that particular thing you must complete in each day, not to have a 6 month delay, for instance. Also, there was the TV show called 1 Day at a Time that ran 1975 through 1984, 1 day at a time. So my lesson was we should plan tasks daily, get things done daily. So I used to get up 3 o'clock in the morning, went to Bell Labs, and I had a daily task for all team members. I assigned the whole team project to individual team members. Before they show up, I placed this assignment on their desk. And then I worked throughout the day to make sure that task is done every single day. That's how we achieved this. And that was a very interesting episode. Sometimes people say, hey, Steve, I cannot do this because my computer doesn't work. Well, I have to take a computer from someplace else and place that on his desk or on her desk to get the a job done on that particular day, for instance. That it was very stressful. I gained my nickname as a Captain Smooth because I managed to, help project flow smoothly. So they called me Captain Smooth at that time. So that was a
Wow.
memorable experience. In terms of computing capability was not enough. Logic design was done in Bell Labs, Homedale. This is a Homedale building. Chip design, physical design was done in Murray Hill here. And massive verification was done in Indian Hill in Indiana, in Illinois, Naperville, Illinois. So was a multi-location project. We had tons of meetings almost every single day. So in summary, we achieved the 6 industry first, full 32-bit internal external data bus, and the high-speed domino circuit was used, invented, twin-top CMOS was used, interconnect-centric logic design was done, gate matrix layout, matrix layout style for high density, and then the instruction support for Unix and the C programming. But more importantly, the trailblazing visionary leadership was important, because when you do certain things first time, everybody is scared and worry about, hey, this is a new design. Is it going to be produced with a good yield and so on? So they had to make a bold decision. In fact, all the CAD tools we had to develop internally, not in Bell Labs, the CAD organization, especially for layout, game matrix layout tool, because they were not ready for that. So we had to, so there is all the saying that if you are really thirsty, you have to dig your own well. That was the situation. We had to dig our own well by inventing gate matrix, automate this layout tools with the software verification, etc., etc. So that was a very memorable experience in that regard. Yeah. So that's the end of my talk.
That's really, really inspiring, Steve. I'm really, I don't know. I don't have words to explain this. The Captain Smooth, one day at a time, and in those days, developing something of this sort was a humongous task. The level of automation and ED, as you mentioned, we have these days compared to what it was done. There's no comparison. It's like I don't know how you could do it. So amazing to know about all the great works you've done, and the inspiring thing is that big physical design which was on the floor, and you're sketching all your parts to find out any broken or not.
Yeah, so
Amazing.
there's an additional interesting story. So we did a design, right, development, and then at that time when design and the initial fabrication is done, the next step is the manufacturing. So we come up with all the documentation of design details, mask data, all that, and then hand over to Western Electric, which is in Allentown, Pennsylvania. We didn't hear anything for several months. So then we were worried, what's happening? Why chip not coming out? We found out that the manufacturing people were saying that chip is too complex, we cannot manufacture. So another big crisis, right? So top boss said, Steve, nothing is more important than getting it manufactured. So he asked me to form a task force, manufacturing task force, report to Allentown, Pennsylvania for production. So we went there and they wouldn't even talk to us. They say, you don't know anything about the manufacturing, so we don't need your help. Practically, I had to sweep the floor to show that how serious we are. We are here to help you, not just commanding you what to do. And after a while, they thought we were serious. We worked together, and then we commuted every single day from New Jersey to Pennsylvania. We left early in the morning, came back at night for several months, and finally we produced more than enough. That was a very memorable experience. From that, I learned a good lesson called the design for manufacturing. For instance, when you are in the lab, you tune the testing machine and you test. So that test result is correct. But in manufacturing environment, you have many testing machines. They are not calibrated uniformly. So you do the testing one machine and the testing another machine. They're different. Yet, in order to do the reliability qualification, you bake pre-oven test and the post-oven testing. They are not necessarily same test machine. So you need a design margin, for instance, statistical design, that sort of things. So that helped me to teach students on manufacturing, design for manufacturing, importance of a design margin, etc., etc. So yeah, that was a good experience as well.
No, that's so interesting, Steve. And I have also worked on DFM, and you know, uh, designing is one part. Ultimately, if that design can't be replicated on physical silicon, then this whole hard work is of no use. And at the same time, while you do so, it's like you want to make apples and you get mangoes. So that is a shift. You always expect a real transistor, a rectangle box, but what you get is a zigzag figure, and at times it is a open or a short, and you always wonder why the circuit is not working. So that shows the depth of dedication you guys had, traveling for months to ensure that's being done. But I should congratulate you and the team. That was worth of efforts you guys have done, all those days doing up and down. And I think that's a worth of a milestone for each one of us to celebrate what was done 50 years back. And I would say that thanks to IEEE CAS even sponsoring this particular part, and ensuring this good amount of effort which was done half a century back by all of you is limelighted, and people are getting to know about it. And I again feel so overwhelmed, and you know full of I would say full of respect for you and to the team who could make almost, I would say, that impossible to be possible in those days. So inspiring. Great. So we still have 6 minutes to go, and I want to give audience an opportunity, though we ask that people can pre-submit the question, and if someone has any question, you can write in the chat window. I will get to know what you are asking for, and then Steve is here to answer that for you. I'm gonna take a quick I would say a 30-40 seconds pause to see if something comes up in our chat box. If not, then I have the most exciting part here to be answered by you, Steve, and I'll utilize that time to ask you those questions.
Okay, sure.
Let me go and check the chat box. Okay, I'm gonna take another 30-second more pause if there are any questions coming from you or from the audience. Okay, seems there are no questions from audience. So Steve, then I have a quick things to ask you, and I call it as I call this as a rapid fire round. Okay, I'm gonna put you on spot for few of the questions I have listed for you, and we would like to. Oh, there's a question. I got a question on the chat. There's a question in the Q&A box, and let me shift to the Q&A box. Great. The first one is from Ivana, and the question is, have you ever had a moment you regretted? Steve, this question is for you. Do you have a moment which you Regretted.
regretted.
It's a tough one.
Many regrets. Yes. So, you know, in my career, I made lots of mistakes, and regretted.
Accepting that in an open forum and that to a recorded forum, I know is challenge.
Yeah. So, I mean, let me tell you one example. For instance, I told you that I entered the Air Force after high school, and then
Mhm.
later I went to college. I was a good student when I was in high school, and my teacher expected me to go to a university directly, but I chose not to. That was my serious mistake, actually. Not going to college first and then fulfill military duty. Usually in Korea, it's compulsory, so you have to go to serve in the military for 2 to 3 years. At that time, I went to Air Force for full 3 years, and right after high school. Even I didn't even attend my high school graduation.
Gosh.
So I was enrolled, and then I had 3 years. So I regretted a lot during that period, but then I managed to take entrance exam right after, from military duty. I was fortunate to enter college with a good grade, good exam score, but it could have been disastrous in that regard. The other mistakes, there are a lot. For instance, when I chose a particular major, I could have chosen in different PhD program, a different track. I chose to do more theoretical aspect of a PhD study. I could have chosen more practical discipline, but at the end, all came together. And I think in your education, nothing is wasted, really. I give you one example. For instance, I did take very difficult optimization courses in graduate school at Berkeley. And I sometimes wondered, well, where am I going to use this stuff? It turns out first year in the labs, I worked on satellite-based private network design, very complex design. I managed to formulate the problem and solve it using optimization knowledge I learned in graduate school. And turned out that was a proof of a decade old the Phillips study practice in network 3-node network design. That actually the optimization result proved that it was optimal design, although it was a heuristic design. So that was very interesting experience, and they realized that indeed nothing is wasted. Really, it all come together. Yeah.
Certainly, and I strongly believe in that, Steve, that no knowledge goes waste when, how, you know, the time tells, but certainly no knowledge goes waste.
Yeah.
Okay. Okay, so in the interest of time, we are already at the hour. I see a question coming from Prabhavati P, that your book on CMOS digital circuit design is still being referred. And I also read it, a couple of decades back. Given the advanced technology node designs in products, how would you advise academicians to relate the theory of industrial practices?
Right. So as I mentioned earlier, it's very important you maintain good contact with the industrial practitioners. I give you one example, for instance. This is more than 3 decades ago. My industrial colleague mentioned that, we have the problem with the heat on the chip, the thermal engineering issue. So we worked on it. We started that research ahead of any other researchers in the field. That was enormously helpful. I mean, it's a still ongoing issue. So it is very important you have your consultant in industry as a professor, for instance. It's good to get to know your industrial colleague and they exchange opinions. So you can have a sabbatical leave in industrial company or invite industry practitioners to research, visit, right? Give a seminar and meet with the graduate student. They can be great mentors for graduate research students. So I think that interaction is enormously important. There are, industry people, they look at the forefront problems ahead of anybody else. They are facing it. It's a good research topic also. So
Great. Thank you so much, Steve. And I hope this question is answered. Okay, so I think we are at the end of the hour of the session, and I see you on the full screen. I don't know, Samantha, if there's something which we need to change on the setting where you can bring at least both of us on the screen. We want to capture that moment before we, close this call with Steve. Whenever I run any IEEE meeting, I do take a screenshot to report it to the V tools, in the system. So Samantha, is that possible that you can bring both of us on the screen, or is it, you can see both of us already on the screen together?
I can see both of you right now.
Okay, great. It's excellent. If you can take a screenshot of that, that would be great. So I want to mention this special thanks to Samantha as well, that she is the one who worked on the background to ensure everything is and everything goes smooth as planned. And certainly next time, Steve, I will again come back to you, with more a variety of questions to learn from all the great experience you have, and certainly this journey of IEEE celebrations and learnings of IEEE Day and the IEEE Week and IEEE History Week keep goes on. Thank you so much from the core of my heart. I'm a big personal fan of you, Steve. I learned a lot from your book, and with all the interactions I had with you all these days, and I missed to see you this year, but I'll make sure I'll see you in person again in the upcoming year. Thank you so much, and thanks to all the audience staying back with us for all the great questions, and thanks to IEEE CAS Society, and especially the our digital communication ad hoc committee who took this initiative for bringing this session all together. Big thanks to Samantha. I know Brittany is not here on the call, but the whole backend team of Circuit System Society to ensure everything runs fine. So with this, thank you so much. We call it as
thank you.
Have a great day, Steve. Really pleasure, honor to stay in touch with you, and I hope the learning continues. Thank you so much.
Thank you. Bye-bye. Bye.
Thanks. Bye bye.